So now we're going to talk about a uniform solid body. For a continuous body, sums are replaced by integrals. Definition: centroid will be at the same location as the center of mass if the body is uniform. In other words, the density is constant. That's supposed to be a rho and not an R, by the way. So that's a mistake in my PowerPoint slide. The Greek letter rho standing for density. Then the centroid, or the center of mass, is going to be, instead of a sum, we have an integral of the position times the differential mass. That'd be like the individual masses of the body. If you multiply this by the acceleration due to gravity, you're going to get a moment. This integral in the numerator, it would give you the moment. And of course, the g times the integral of dm will give you the weight. Well, you can replace dm, differential mass, with density times dv, density times differential volume. And then the densities factor out. You're left with this expression, which is the centroid. Similarly for y, similarly for the z, same thing. If a body has a line of symmetry, this body has two lines of symmetry. The center of mass is on that line. So the right side is a mirror image of the left. So that means the center of mass has to be on the y-axis. The top side is a mirror image of the bottom, which means the center of mass has to be on the x-axis, or right at this point. These are just like distributed loads that we dealt with in chapters 4 and chapter 7. Okay, let's go on to the next slide. There we go. So here's an example. A parabolic arc, y equals x squared, so we want to know what is the center of mass of this body. And we get a differential L, and we express it in terms of the differential x and differential y. dx and dy. dx back and forth, dy up and down. Root. So we can also get dx dy. Well, x equals y squared, so dx dy is going to be 2y. And then we'd square it. So here's the 2y squared. dl equals 2y squared plus 1 dy. And then we can get the location of the centroid. So this x tilde is just the variable of integration. We're going to be integrating over the line the x coordinate at that location times dl. We've already expressed dl in terms of dy. And one more step, x equals y squared is right here. So now we got an integral strictly in y. Then the integral of the total length is just this part of it, just the dl part of it. Okay, look up those things on the integral table and plug and chug your numbers, and you get this number. Very similarly for y. Now, you don't have to, since you have an x here, x equals y squared, you got that conversion here, you don't even have to worry about it. And then the integral dl is the same as it was before. So now we've got the location of the center of mass of that object. Okay. Circular wire. This one has a trick. It's kind of a neat trick, actually, that you can put things in polar coordinates. So r d theta is dl. And here's the x-coordinate and the y-coordinate, the variables of integration in r cosine theta and r sine theta. So you can just plug and chug into our formulas. So the integral x bar, so cosine squared dl r d theta. The integral from 0 to pi over 2 of the cosine theta is going to be 1. The integral from 0 to pi over 2 of d theta is just pi over 2. So it's r squared divided by pi over 2r. Well, flip the denominator and multiply, and you get 2r over pi. Y bar, exactly the same calculation, except this time you have a sign here. Well, sine starts out at the integral of sine is the cosine. Oh, excuse me, negative cosine. Negative cosine. So cosine of pi over 2 is 0. Then you subtract the negative cosine, in other words, you add, of 1. A negative cosine of 0, which is 1. And you get the same answer. Symmetric. There is a line of symmetry in this guy at 45 degrees. So you'd expect it. The center of mass has to lie on that 45 degree line. So look for symmetry where you can. So we're going to look at the triangle now, which we've done before. So y equals h over b times b minus x. Here's the xy coordinate. Here's the center of mass of this differential area. The differential area would be x dy. The center of mass of that area would be right here. So we can integrate from 0 to h, for example. And here's the y formula and dy. Okay. So dA, x dy, just like we talked about. We're solving for x right here. B divided by h times h minus y, that's solving for x. Okay. Yeah. What is the x coordinate? Express x, this x right here, this location, this, excuse me, this x at this location in terms of the height. So we get h minus y dy. Let's go figure this out. Okay. So we have y equals h over b times b minus x. Sometimes you got to do a little algebra to convince yourself. Y equals h over b times b minus x. So now we have to get this in terms of y. Oops, wrong, didn't want to do that. Okay. H over b times b minus x. H over b times b minus x. There, triple dots, by the way, mean therefore. Therefore, by equals hb distributing this minus hx. Therefore, x is going to equal to b times y minus h, h minus y, excuse me, other way around. All divided by h. Is that the formula we get? Comparing it? Yes, we do. So that's what x equals. The centroid, they're using this tilde to mean the centroid of the differential. And this is the variable of integration. Okay, so now that we have everything, so we have to do y times dA. Well, we've got x in terms of y, so let's look at the integrals. Y times x dA, and there'd be a dy, or there's a dy right here. It's inside the brackets. It's not outside. I was expecting it outside. Integral dA. So work that out. And again, sometimes you just got to convince yourself. So you have b over h, distributing this times h, times y dy. That's supposed to be an integral sign. Minus b over h y squared. Dy. B over h, y times y, dy. Okay. Area is 1/2 base times the height. You guys know that stuff. Don't need calculus for that. 1/2 base times the height. So, well, that'll cancel out. That'll cancel out. Something's wrong here. B over h. Oh, I forgot an h here. Oh, no, I didn't. No, I didn't. I'm fine. I'm fine. Equals b y squared, or when you do the integration, by squared over 2, and the limits of integration, h. So it's bh squared over 2. I tried to change it. Minus b over h, and that'd be h cubed over 3. All over 1/2 bh. Which is going to equal, so I have bh squared here, bh squared here. It's going to factor out. That's the bh squared. 1/2 minus 1/3 is 1/6. So voila, we got it. H over 3. And we learned that from distributed forces before. Now, the centroid of a quarter circle, you'd find much the same way as we found the centroid of a full circle. And my time recorder says that I should probably stop right about here. We'll pick this up next time.